We'll now talk about the phase behavior of mixtures that are entirely liquid. And so, to go through this, let's first consider a model system. And so we're going to talk about a binary mixture, so two components, that phase separates into two regions. And the classic example or the classic model system for this is going to be the mixing of oil and water. And so you've probably seen this, whenever you try to cook. And if you ever tried to mix cooking oil with water, you probably saw that the oil and the water don't form a clear liquid or a clear solution, but rather the oil and water kind of separate themselves into two distinct regions, where this top part is oil and this bottom part is water. And even if you shake up the mixture, shake it up very hard as you can, you see that the oil never really dissolves in the water, but rather you end up with just kind of like tiny droplets of oil dispersed in the water. And eventually, if you wait long enough, the oil will return back to the top of the liquid mixture. Okay? And so that is an example of liquid-liquid phase separation. Okay? And so if we drew this schematically, in an oil-water mixture, you see something that looks like this, where you have two domains, where the top domain is what we call oil-rich, and the bottom domain is water-rich. And the reason the oil domain is above the water domain has to do with density. Typically, oils are less dense than water. Now, you'll notice that I've used the word oil-rich and water-rich rather than just saying this is the oil domain and this is the water domain. And that's because even though, oil and water don't like mixing with each other, so although oil and water are immiscible, which is just another way to say don't mix. If you have a mixture of the two, the top domain is not going to be entirely oil, and the bottom domain is not going to be entirely water. So neither phase is pure, if you will. And that's because in order to, sort of maximize the entropy in the system, there's always going to be some oil molecules, not a lot, but just a couple, that dissolve in the water domain, and a couple of water molecules that dissolve in the oil domain. So there is always some solubility. And so in the oil domain, you would have some liquid mole fraction of the oil, which is probably really large, but then also some liquid mole fraction of the water. And similar in the water-rich domain. Okay? Now this solubility of each of the species in each of the domains is going to depend very greatly, very significantly on temperature. And also a little bit on pressure, but not that much. And so when we're talking about liquid-liquid phase separation, in contrast to the vapor-liquid equilibrium, for liquid-liquid, we're just mostly going to focus on temperature as our variable. And so we're going to look at a lot of TX diagrams. Okay? Now, with these liquid-liquid mixtures and liquid-liquid phase separation, what we're going to look at a lot is what's the molar Gibbs excess energy in the system. And so if for a liquid mixture, if the excess Gibbs energy is greater than 0, that would mean that the miscibility, or the ability for the chemicals to dissolve in one another, that's going to increase with temperature. And conversely, if the excess Gibbs energy is negative, the miscibility will decrease as you increase temperature. So T going up. Okay? And so graphically, that would look like this. So let's look at the case where the excess molar Gibbs energy is positive. Okay. All right. And so let's say we start off at a very high temperature. Okay. So somewhere up here. So at this high temperature, the mixture is going to be in one phase. Okay. So if you made a solution, it would just look like pretty uniform throughout the entire mixture. But then, let's say we start off at this high temperature, and then we cool the mixture down. As we cool the mixture down, eventually we will reach some sort of critical temperature, where below this critical temperature, we won't have one phase anymore, but rather the mixture will phase separate into two phases. And the window for this two-phase region will look something like this. Where as we cool down, so let's say we were at some original mole fraction, as we cool down, as we get into this two-phase window, the mixture will then separate into two regions that have different mole fractions. Okay? Alright, and since species 1 is the oil, for the region where the mole fraction of oil is relatively low, we would call this the water-rich region. And for the part of the phase window where the mole fraction of oil is very high, we would call this the oil-rich region. Okay. All right, and so outside this little upside-down parabola, so at high temperatures, the mixture just forms one uniform phase, and then if you go below some critical temperature, then the mixture starts forming two different phases. All right, and so we would call a mixture that exhibits this sort of behavior, we would call it an upper critical solution temperature. And so upper means if you go above some critical temperature, then your solution is always just going to be one phase. So phase separates as T decreases. And so another way to say this is that as you heat the mixture, both of the species in the mixture become more soluble in one another, until you go above some temperature where all the species are going to be completely soluble at any composition. Okay? And so, that kind of makes intuitive sense. As you heat things, they mix better. Right? And I would say that the upper critical solution temperature is your most common behavior that's seen for liquid mixtures. But of course, there's always exceptions. And so now let's talk about the case where the excess Gibbs energy is below 0. And so in this case, in your TX diagram, you would see behavior that looked like this, where at some low temperature, you have your one phase region, but as you heat the material, it becomes less miscible. Both the species become less miscible in one another until you reach some critical temperature, in which above that critical temperature, the mixture will phase separate, and you reach the two-phase window. Okay? And so this type of behavior is known as a lower critical solution temperature. Such that if you go lower than that critical temperature here, then your system will be completely miscible in one another. Right? And so for this system, it phase separates as T increases. Right? Now, this sort of behavior may be less intuitive. It's less, and it's also less common. And in order to get that to happen, you need very specific type of molecular interactions between the species and the mixture. But I would say that these sort of systems are desirable for many applications. And in fact, in the biomedical field, folks spend a lot of time trying to design medicinal or therapeutic systems that do just this, where at low temperatures, in order to make things easy to process, they keep everything in one phase. But when they actually go deliver it in the body, which is at a slightly warmer temperature, the system will then be able to phase separate into a particular structure. Right? And so that's the thing I want to emphasize, is that it's important to understand the phase behavior of these liquid mixtures, because the mixture that is, in one phase that's completely uniform throughout is going to behave much differently and have different properties than the mixture that phase separates into two or more phases. Okay? And so, in the following videos, what we're going to do is we're going to go through and establish a quantitative framework for understanding and predicting the phase behavior of liquid mixtures.